Hi, my name is Ram Prasad, and this work is casting your model, learning to localize improve self-supervised representations. Contrast with self-supervised learning, SSL aims to learn visual representations from unlabeled images through the task of instance discrimination. While some of the recent methods have begun to outperform fully supervised ImageNet retraining on several tasks, unfortunately, their success have been confined to unlabeled ImageNet images, and the naive application of these approaches to uncurated web images have only shown marginal gains. In this work, we analyze contrastive SSL approaches to understand the cause of this limitation. We find them to have poor visual grounding ability. In this example, when we use GradCam to understand which regions the model relies on when matching the query and the key representation, the model seems to look at the grass regions more than that of the dog, leading us to realize that these models may be relying on low-level visual cues or spurious background correlations. Even during the crop computation stage, where taking random crops from an image may be acceptable for iconic images, however, for scene-level images such as this, they might receive imperfect supervisory signals because they contain different visual concepts, and this discourages semantic understanding. To fix, to fix this, our first contribution is a semantic alternative to random cropping. We devise an intelligent geometric transform for cropping different views from an input image based on area constraints from an unsupervised saliency map. This leaves us with two crops that have salient regions common between them and crop-oriented saliency maps which can be used as supervision. Here you can see how constraining crops through saliency maps leads to improved crops over random crops, especially on complex scene level images. We now turn to our approach cast, contrastive attention supervised tuning, where the idea is to make models attend to appropriate salient image regions during contrastive pre-training stage. We show cast in the context of MoCo. Given an image and its saliency map from deep USPS, through our saliency constraint random cropping strategy, we get query, a key crop, and crop-oriented saliency maps. We can pass the query and the key to their representative encoders. The momentum contrastive loss tries to get the query and the key representation closer, but farther away from a queue of negatives. With the masked key containing just a salient region in the key crop, we can compute the gradient of the dot product of the query and the masked key representation with respect to the last convolution layer of the query encoder. We global average pool the gradients and combine them with forward activation maps to get GradCam. As we can see, the model looks at the background regions and not the sheep as we would have liked. We hence provide a cosine similarity based attention loss to align GradCam map with query aligned saliency map. These two losses are combined to form our cast loss. The model upon convergence now looks at the sheet when matching representations of the query and the key image. In addition to outperforming MoCo on all tasks, linear and fine-tuning, we find that class pre-training on COCO, which is a 10x smaller dataset, even outperforms ImageNet fully supervised pre-training on the fine-tuning tasks. We find that the improved grounding during pre-training transfers to downstream tasks as well. Note how the ImageNet fully supervised model and MoCo uses the background as well to predict ball player, whereas the cast pre-trained model only looks at the player. We find that cast models attend to the whole extent of the objects. To test the robustness of cast, we evaluate on the backgrounds challenge dataset, where the backgrounds of ImageNet images are replaced with various settings. As can be seen, cast pre-trained models significantly outperform on all the settings. For this image of a bird, when the background is changed from sky to water, the baseline model changes its prediction to fish, whereas cast pre-trained model still predicts bird, indicating its reliance on foreground regions more. Similarly, when the background of this reptile class is changed to a place where musical instruments typically occur, the prediction of the cast pre-trained model does not change as opposed to MoCo. In this work, we identified issues with contrastive SSL approaches that prevent them from learning representations from complex scene-level images. We introduced cast as a way to enable learning from uncurated web-scale datasets in the future. Our code, models, and the paper can be found in the QR code links. Thank you and have a great CVPR.